Hello students and welcome to the stoichiometry lecture. Stoichiometry is probably one of the most important and most applied concept that you will be using in general chemistry and even later in organic chemistry. So it's really based on having conversion factors, or what we call the mole ratio, that is derived from the coefficients in balanced chemical equations. So the key here, we always have to have our chemical equation balanced. So let's read this. If we have 3 moles of nitrogen gas and more than enough hydrogen gas, how much ammonia can we make? So it will allow us to predict the amount of product formed or how much even of the reactant did react. So if I have 3 moles of nitrogen, this is here, I first check for my chemical equation, and my equation is absolutely balanced. 6 hydrogens in, 6 hydrogens out, 2 nitrogens in, 2 nitrogens out. So if I start with 3 moles of nitrogen, how much ammonia I'm going to be forming? So this is where we have what we call a mole to mole ratio. We know from the balanced equation that 2 moles of ammonia form from 1 mole of nitrogen, right? We have this in our balanced equation. 2 moles of ammonia will come all form for every 1 mole of nitrogen. So this is what we call the mole ratio, and let me go back for a second and add something to that. So I also can say 1 mole of nitrogen is needed to form 2 moles of ammonia. So we can use any mole to mole ratio and use it or write it in 2 conversion factors. We end up using the one we need for a given problem. Now, first thing first, we always need to write balanced equation. We go for the mole. What does that mean? Mole is the core of your calculation. Stoichiometry depends on what we just mentioned, mole to mole ratio. So to perform stoichiometry, we have to have the moles. So if they give you mass, you convert it to moles. If they give you number of atoms or molecules, you convert it to moles, and so on. You need to find the moles of the desired substance they are asking, and then we convert mole into proper units. So here is an example. Methanol burns in air according to the following equation. 2 moles of methanol reacts with 3 moles of oxygen to give me 2 moles of carbon dioxide and 4 moles of water. If 209 grams of methanol are used up in the combustion, what mass of water is produced? So let's try to work on this problem together. They gave me, here is how I like to explain stoichiometry. They gave me information about methanol. In this case, it was the mass, and they want information about water, which is what stoichiometry is all about. If I know information about one reactant or one product, I can get information about the rest participants in the chemical equation. Okay, so we're going to start with 209 grams of methanol. This is what they have given me. What did we say? We go to the mole. So we convert that into mole, and we say 1 mole of methanol have a molar mass of 32.03 grams of methanol. Now I want to go to water. So what I do, I take the mole to mole ratio. Right? I mean, grams of methanol canceled out. I want to cancel moles of methanol. And I want to get moles of water using the mole to mole ratio. So what I know, for every 4 moles of water formed, 2 moles of methanols were used, right? This is here again our mole to mole ratio. Finally, if they want the mass of water, then I have my last conversion factor. I can say there is 18.02 grams of water for every 1 mole of water. Now I am looking at my numbers. Clearly I need to have 3 sig fig. If I log in the numbers into my calculator, the answer will be 235 grams of water will form. This is here a very good, simple, yet comprehensive example of applying stoichiometry to a balanced chemical equation. Use the following equation. 2 moles of nitrogen monoxide reacts with oxygen gas to give me 2 moles of nitrogen dioxide. How many moles of nitrogen dioxide are formed by the complete reaction of 0.254 moles of oxygen? Again, in this case, it's kind of easy. They gave us moles and they want moles. So we're going to start with what they have given us, which is 0.254 moles of oxygen. They gave me information about oxygen and they want information about nitrogen dioxide. So what is the mole to mole ratio? 2 moles of nitrogen dioxide will form from every 1 mole of oxygen gas. And since they only want moles, I am done with my conversion factors, right? All I have to do is to do the math here, and the answer will be 0.508 mole of nitrogen dioxide. All right, so that's a very simple example here because they gave us the moles. Let's look at the next one. Now, how many grams of nitrogen dioxide are formed by the complete reaction of 1.44 grams of nitrogen monoxide? So this time, they gave me information about nitrogen monoxide, but they want me to get answers about nitrogen dioxide. So again, I'm going to look at what I have here. I have 1.44 grams of nitrogen monoxide. I take it to the mole. I know that 1 mole of nitrogen monoxide has the molar mass of 30.01 grams of nitrogen monoxide. Then I take it to mole ratio. From my balanced equation, I can see that there are 2 moles of nitrogen dioxide that are going to form from 2 moles of nitrogen monoxide. Now I am ready to do my math and I need to present my answer in a 3 sig fig. And that will give me number of moles here. So I'm going to just stop here just in case I need number of moles, because you will see why in the next example. 0.0480, and that will be moles of nitrogen dioxide. However, they want the grams, so I just continue with my next conversion factor, and I will say 46.01 grams of nitrogen dioxide for every 1 mole of nitrogen dioxide, and the final answer will be 46.01. It will be 2.21 grams of nitrogen dioxide. Okay, now sometimes it will be helpful, not always, like, to get the moles in the middle. It will be very helpful if we are figuring out limiting reactants, as I will show you in the next slide or so. All right, so now let's move to the next one. How many oxygen molecules are needed to react with 3.46 grams of nitrogen monoxide? Again, don't be upset or scared when you see that they start to change things on you. So now they want something different. However, stoichiometry in principle is the same. They gave you information about nitrogen monoxide and they want information about something else in that equation. That's okay. Same strategy. We always go to the mole. So what we have here is 3.46 grams of nitrogen monoxide. I go to the mole. 1 mole of nitrogen monoxide has a molar mass of 30.01 grams of nitrogen monoxide. Now I go mole to mole ratio with oxygen. I know there is 1 mole of oxygen reacting for every 2 moles of nitrogen monoxide. Then after that, I know now that I can convert moles of oxygen to number of molecules using Avogadro's number. So what I will say, there is 6.022 times 10 to the power 23 oxygen molecules for every 1 mole of oxygen. Again, I will have 3 sig fig in my final answer. And the answer will be 3.47 times 10 to the power 22 oxygen molecules. All right, so let's now go and talk about limiting reactant concept. So I want you to look at this picture. In this picture, we have 10 molecules of hydrogen gas reacting with 7 molecules of oxygen gas to give me 10 molecules of water. However, 2 molecules of oxygen are left out, did not react. If I'm asking you why did that happen by just simply looking at the picture, you will tell me, well, those oxygen molecules don't have any hydrogen molecules to react with them. So the amount of water was limited by how much hydrogen I have. I have extra oxygen, but hydrogen limited how much water I can get. And therefore, in this specific example, hydrogen is the limiting reactant and oxygen is the reagent in excess. So the excess reagent is portion of the reactant that is or are left over. The limiting reagent is the one that used up first and it limits the amount of product formed. Here is an example. You probably can do limiting reactant in your own home with simple thing like making a cheese sandwich. So if your recipe for the cheese sandwich is to have 2 slices of toast with 1 slice of cheese, then you went to the refrigerator and you found in this specific example that you have 2 slices of cheese and 6 slices of bread. Immediately you know, well, based on my recipe, the maximum I can make today will be 2 sandwiches. I will have extra bread, but all the cheese will be consumed. So you just did limiting reactant by looking at a very simple example, right? You can find the limiting reactant in chemical equation by first starting by balancing the equation. Then assume each reagent is completely used up and calculate how much product is formed. The limiting reagent yields the smallest amount of product. All right, so in chemical equation, we also care about calculating the yield. Like if you are carrying a chemical reaction in the lab, I will care about how much product did you form, what was your yield. So a theoretical yield is, in theory, there is a maximum amount of product that is possible. And that's because you will always have a limiting reactant that will limit what can you have. What is the max you can have, right? So the theoretical yield is the maximum amount that you can possibly have. And it's always, always limited by the limited reactant. It's always based on the amount of the limiting reagent. However, in life, let's say theoretically, you could make 10 grams. You go to the lab, chances are you will never make 10 grams because there is no perfection. Things can go wrong. There are always many sources of human errors, instrumental errors, multiple sources of errors. So what we end up having is something, and it has to be lower than the max. So if the max you can possibly get in the lab is 10, you can never get 11, but chances are you will get 8, 9. The 8 or 9 is what we call the actual yield, is what you actually will obtain in the lab. This is here an experimental number, right? It cannot be calculated, unlike theoretical yield, which can be calculated by the limiting reactant. The efficiency of the reaction, how well your reaction went, is calculated by what we call a percent yield. Percent yield is the actual yield divided by theoretical yield, and this is then multiplied by 100%. So how much you got, in relative to what you could possibly have gotten, right? And then you multiply this by 100%. The higher the number, the better your reaction, the outcome. So here is a big example. Let's read this example together. And suppose 50 grams of aluminum and 75 grams of hydrogen chloride react to form aluminum chloride and hydrogen gas. Which reagent is limiting, and how many grams of hydrogen gas are produced? How many grams of each reagent remains? And if 1.92 grams of hydrogen was actually formed, calculate the percentage yield. All right, so I always give this tip for my students, so please make sure that you are listening. In any question, you need first to look at your chemical equation, okay? If they end up giving you quantity of two reactant, now I'm gonna remind you, okay? So remember, this part here is the reactant part. And this part here is products. If they ever give you quantities of two reactants, that means you immediately have to figure out what is your limiting reactant. Okay? So now let's go back. And look what they gave you. 50 grams of aluminum. This is a quantity of one reactant. 75 grams of hydrogen chloride, another quantity of another reactant. And the reason why I'm saying quantity, I'm being careful here because it could be mass, it could be number of particles, and if it's a solution, it could be volume and concentration, right? Anything that can yield moles is a quantity, right? It can be mass, it can be number of atoms or number of molecules, and it also, if it's a solution, it can be volume and concentration. So, also, I'm going to bring your attention to the following, and I want you to pay attention. So, in normal question in chemistry, you are not going to be guided this way by telling you which reagent is limiting, right? I'm writing here because this is your first exposure, so I'm trying, to show you the systematic way. But in a normal question, they will immediately jump on how many grams of hydrogens are produced. They're not going to mention which reagent is limiting. They will assume that once you saw that they have given you quantities of two reactants, you will have to figure out the limiting reactant. All right, so if I am solving this question, all what I'm going to do, I'm going to say, all right, first thing first, I will say, find the limiting reactant. And since they want questions about hydrogen, so I will use hydrogen as my way to get the limiting reactant, right? I'm gonna test aluminum and test hydrogen chloride and see which one will give less product, and that will be my limiting reactant. So I start with aluminum. I'm gonna say, okay, 50 grams of aluminum, when it has to be converted into moles. 1 mole of aluminum has an atomic mass of 26.98 grams. And then I'm gonna go to hydrogen again, because they're asking about hydrogen. Why waste my time, right? There are 3 moles of hydrogen gas for every 2 moles of aluminum. Now, pay attention. I already have checked that my equation is balanced, right? That's something that's very important. Now, I can get to the mole, or I can just do one step and go to the grams, since I'm going to get to the grams anyways. And I'm going to say, all right, there is 2.02 grams of hydrogen gas for every 1 mole of hydrogen. And now look at the answer. That will be in 3 sig fig. The answer is 5.61 grams of aluminum. Now I'm going to use the same thing, but this time for hydrogen chloride. And I'm going to say, okay, 75.0 grams of hydrogen chloride. I will go to the mole. 1 mole of hydrogen chloride has a molar mass of 36.46 grams of hydrogen chloride. I go to my mole to mole ratio. There are 3 moles of hydrogen forming for every 6 moles of hydrogen chloride. Then I do the mass, 2.02 grams of hydrogen for every 1 mole of hydrogen. When I do the math here, taking into account the 3 sig fig, the answer will be 2.08 grams of hydrogen gas. And this is also, that's so sorry for that, is hydrogen gas. So now, okay, here is how I can verbalize what does that mean. If I used all my aluminum, I'm gonna get 5.61 grams. If I used all my hydrogen chloride, I'm gonna get 2.08 grams. So I'm gonna go back to the sandwich thing. If I used all my bread, I'm gonna get 3 sandwiches. But if I used all my cheese, I'm gonna get 2 sandwiches. So how much I'm gonna get at the end of the day? Cheese limited me, right? 2 sandwiches. Same thing here. This limited me, so this is what I'm gonna get. This is the max I can get, because I'm gonna make a conclusion. Hydrogen chloride is the limiting reactant. And that here is called theoretical yield. All right. Now, let's go to the next question. How many grams of each reagent remains? All right. So, when it comes to HCl, it is my limiting reactant. That's the easiest one to answer. From HCl, 0 will remain. And the reason for that, because it is the limiting reactant. All of it was consumed. Now, for aluminum, I need to know how much did react. Who is going to control how much of those 50 grams of aluminum reacted? How do I know how much of it did react? Hydrogen chloride, the limiting reactant, control how much of it. So what I'm gonna do, I'm gonna use here, so I'm gonna change my color, and I am going to use this here. I'm gonna say, okay, if I used my 75 grams of HCl, and I'm gonna convert that into moles, 1 mole of HCl does have a molar mass of 36.46 grams of HCl. Convert that into moles of aluminum. 2 moles of aluminum for every 6 moles of HCl, and then multiply that by the mass of aluminum, which is 26.98 grams of aluminum for every 1 mole of aluminum. The answer will be 27.75 grams of aluminum, and here is the keyword, reacted. Okay, this is how much aluminum reacted. They're not asking about how much aluminum reacted, they're asking about how much of it remained. So aluminum remained will be what I started with, which is 50.0 grams minus 27.75 grams, and the answer will be 22.3 grams of aluminum left. All right. So again, 22.3 grams of aluminum left. That's the aluminum remained. Now the last question, if 1.92 grams of hydrogen was actually formed, calculate the percentage yield. And the way I'm going to calculate the percentage yield, now remember, I'm going to first erase. Let's erase this part here. And now I'm going to calculate the percentage yield. So percentage yield is equal to actual divided by theoretical multiplied 100%. So what was my actual yield? It's given to me here, was actually formed. That's something I cannot calculate. It's 1.92 grams. Theoretical yield, remember, is 2.08 grams multiplied by 100, and the answer for that will be 1.92 divided by 2.08 multiplied by 100 will be 92.3%. I hope you had a good understanding of how you address stoichiometry and limiting reactant in a question like that. Again, like this is like something you should expect in a quiz, you should expect in an exam. I'll definitely will be asking you a stoichiometry limiting reactant question. Now that you have seen this full example with me, I have provided an example for you so you can practice what you have learned in this slide. So here is an example for you. In one process, 124 grams of aluminum reacted with 601 grams of iron 3 oxide, according to the following balanced equation. Which reagent is the limiting reagent? Calculate the mass of aluminum oxide formed. How much of each reagent is left? And if only 156 grams of aluminum oxide was actually formed, calculate the percentage yield. So you can pause this video right now and start working on this question. Thank you, and I will see you in the next lecture.